Next up, we want to look at the behavior of natural radioactive particles in electric and magnetic fields. Their behavior was first discovered by Ernest Rutherford's experiment, the British physicist. This experiment gave us an overview of of everything, the general properties of these particles, their speed, their mass, their polarity, their everything. And examiners love asking questions around this. So, these were the first experiments to verify their behavior in electric field. So here the radioactive substance was placed here in a lead shade, and it was meant to pass through the electric field, as you can see here. And while passing, it was observed that one of them passed up straight up without deviating and also penetrated the photographic plate. The other one passed and was deviated to the negative terminal of the plate. The other one was deviated towards the positive terminal. And this was how they got their names and their polarities. You know, in electricity, positive and negative charges attract each other, while similar charges, plus plus or negative negative, repel each other. And then when there is no a charge, when there's no charge, when there's charge neutrality, there's no attraction or repulsion. And so the gamma rays or the gamma radiation exhibited this neutrality. And so it is proclaimed or pronounced a neutral radiation, as you can see here. Then the other one deviated toward the negative, and that was the alpha particle with the helium nuclei. With the helium atom. Look at it here. And then the other one deviated to the positive, and this was the beta particle. And so for this reason, we said the beta particle has a negative charge, while the alpha particle has a positive charge, and the gamma ray or the gamma radiation has no charge. Their behavior in magnetic field was also similar. So in magnetic field, this was their behavior. The radioactive substance was also placed here and was meant to pass through the north pole and the south pole, and then the north pole of this magnetic field. And it was meant that the gamma radiation also showed no deviation in the magnetic field. And then the alpha particle deviated toward the south pole, and the gamma and the beta particle deviated toward the north pole. So we can say, with this, we can summarize their behavior, and this is very, very important. They may ask you to draw this diagram or this diagram, or explain their behaviors in both fields, and this is how to go about it. So at this point, I would like us to look at their general characteristics as summarized in this table below. So this is the radiation, and this is the type of radiation: the alpha particle, the beta particle, and the gamma rays or gamma radiation. For nature, it is the helium nuclei. And velocity, 5 to 7%. So the alpha particle has a velocity of 5%, 5 to 7% that of the speed of light. Polarity of the alpha particle is positive. The charge of the alpha particle is 2 electron, and 1 electron is equivalent to 1.6 exponential negative 19 coulomb. And so 2 of that is 2 multiplied by this figure, will give us this figure here. The mass of the alpha particle is relatively massive. Deflection if effect of electric field on this charge on this particle, and also effect of magnetic field on this particle. You saw it in the diagram we just projected uh, previously, and this is what we saw there as summarized here in written words now. Ionizing power, large and cause heavy ionization. Penetrating power, it has little or even no penetrating power and can only penetrate thin sheets of paper. Fluorescence causes fluorescence in zinc. So for the beta particle, this is what we have here. That is the atom represented by the electron, zero mass number, -1 atomic number, and it travels at approximate speed of light. The charge is the polarity is negative, and the charge is 1 electron, as can be seen here. It is relatively light. Its behavior in electric and magnetic field is summarized here and here. Ionizing power, medium, about 0.1% of that of alpha particle. Penetrating power, good penetrating power in air, several millimeters of aluminum. Fluorescence, it has no fluorescence in zinc. Next up is the gamma rays or gamma radiation. The nature is this: the speed, it travels at the speed of light. The gamma ray or the gamma radiation is an example of electromagnetic waves, and all electromagnetic waves in their EM spectrum, they have some stuff in common and some stuff not in common. For instance, all of them in that spectrum travels at the speed of light. All of them in that spectrum, they are all transverse waves. All of them in that spectrum, they have different frequency of vibration and different energies and different wavelengths. So these are the stuff that they have not in common. And then the charge, it is electrically what? Neutral. For the polarity, it has no negative or positive. It is just neutral. So with the charge, it is electrically what? Neutral. The mass is very, very negligible. And effects in electric and magnetic field, it has no effect in both electric and magnetic field. Ionizing power, very small ionizing power, and penetrating power, very, very high penetrating power. Why is it so? Because the wavelength of this guy is very, very short, and all electromagnetic waves with short wavelength have very high penetrating power. So this table is very, very, very important. You can memorize this table. Examiners may put this table before you and ask you to fill in the blank spaces, and you should know what and what to fill in appropriately. Thank you. Next up, we want to look at the nuclear equation for the alpha, beta, and gamma radiation. So we have explained what this symbol means previously, and these are not strange to us right now. This is the representation of the alpha particle. We omitted an E here, but you can write that if you want to. And so we have the 4 as the mass number, and then the 2 as the atomic number. And so what we are trying to explain here is that this particle is a radioactive particle, and this particle disintegrated in the bid to gain stability by emitting an alpha particle here. And a new atom was formed, and then plus a release of energy, and this is equation 1. Next up, this is representing a radioactive atom or element. In the bid to gain stability, it disintegrated and emitted a beta particle, and then a new atom was formed plus energy, and this particle that was released was a beta particle. And this is typical for natural radioactivity. Examiners may present these nuclear equations to you and ask you to distinguish if they are natural radioactivity or artificial radioactivity. We are going to explain all that in this session. So for the gamma radiation, this is what we have. The particle in the bit to gain stability disintegrated to form this, and then plus energy was released. So gamma radiation, gamma is a form of light emitted as photons of energy, HF, where H is the Planck constant and F is the frequency of radiation, and as zero mass number and what zero charge. And this is what we can see. Natural radioactivity. This is another example of natural radioactivity: alpha decay, beta decay, and gamma emission or gamma decay. You can see what is here. The parent atom or the parent nuclei was disintegrated, and then a new one was formed, and then an alpha particle was released here. This is the alpha particle that was released. Look at it here in pictorial representation. So this one was a beta decay. This is the parent or the original atom. And one of the things that causes disintegration or decay of an element is, there are just two. You can make more research about it: the heaviness of the nuclei of the atom, and then instability. There are some atoms that are stable in nature. Those ones don't undergo radioactivity. Highly unstable atoms and atoms with very heavy nuclei are liable to undergo radioactivity. So this is one thing that you need to know about this here. So this one, this is it here, and then it was emitted a gamma ray. You can see that here it has zero mass and then zero atomic number. Thank you.